Hello and welcome to this lecture. We are going to continue studying second order linear ODEs with constant coefficients, and now the non-homogeneous case where you have a forcing function and this forcing function q of x may be some function. Okay, so we won't consider all possible functions, we will only consider a few specific cases and which are relevant for circuit solving and all that. Okay, so that's what we'll consider. Okay, so here is an important property. It's an easy enough property to prove, and this is particularly useful in the solution. Okay, so supposing you find by some method, okay, some guesswork, some luck, some some chance that you find one solution for this equation. Some one solution you find. We'll show you how finding one solution may not be that difficult using the properties of functions that we know. Okay, so I'll motivate that for you. So let's say you find one solution. Somehow you found one solution. Okay, let's assume that. What you can do, interestingly, is you can take another solution for the homogeneous case. Right? This is a non-homogeneous case, so it's equal to q of x. Let's say I forget about q of x being some other function. I make it just 0. I take another solution to the homogeneous case, and guess what? This is what's most interesting. In that case, g of x plus h of x becomes a solution for the original non-homogeneous equation. This is actually very easy to prove. You put f of x equals g of x plus h of x. These derivatives, all the left hand side will become this with h plus this with g. But this with h is actually 0. This with g is actually q of x. So h of x plus g of x is a solution here. Okay, so this is actually, you should remind yourself of one of the very nice properties you have. One of the very nice properties we had when we solved linear equations, right? Just set of linear equations. We used something like this. We found the homogeneous case equation, and every solution for the non-homogeneous case you can add to that, some null space and all of that we used sometimes. So this is actually very reminiscent of that. You make the right hand side equal to 0 and you see how these solutions come about. So a lot of these ideas are sort of foundational and fundamental, and they keep coming up again and again in this situation. So I know the family of solutions to this homogeneous equation. I know one solution to this non-homogeneous case. I can get a family of solutions to the non-homogeneous case also. Okay, so you see how we solve the simple problem, and then we are trying to solve the more complicated problem by using the solution for the simple problem. The essential same methodology appears again and again. Okay, so h of x is solution of homogeneous equation. We can find general solutions. G of x is called a particular solution, one particular solution. But how do you get the particular solution? Okay, so I'll show you. It's not too bad in many cases. Okay, so you have to guess, right? So you have to sort of guess based on these functions, right? For instance, just look at this function, right? Supposing q of x is a constant, supposing q of x is 4 or 5 or something. Okay, what is a reasonable guess? Just look at this. What can you guess for f of x? I want a constant here on the right hand side. What would you guess? Okay, a very simple idea you can see. I may guess f of x is some other constant, right? See, if I guess f of x is some other constant, these guys will go off to 0, no? Constant derivative is 0. I know that is true. So some other constant times c is equal to this constant. I can solve for that constant. So I'm able to quickly find a particular solution very easily if it's a constant. So like that, we will try and motivate a particular solution. So this is doable. So first case is when q of x is d, which is a constant. Okay, some constant number d. The guess which works here is f of x equals e. Some other constant. E is maybe I shouldn't use e. E is not the exponential here. So e is just some constant real number. So here is an example. If you have f double prime plus 2f prime plus 5x equals 5f equal to 4, I may guess f of x equals e. I get 5e equals 4 because this derivative is 0, this derivative is 0, 5e equals 4 or e equals 4 by 5. Okay, once again remember this notation is slightly confusing. So this is not the 2.71 that number, this e is just some constant. Okay, so I'm guessing that constant. I get e equals 4 by 5. So if I put 4 by 5 for the function f, I have a solution for this equation, right? So a particular solution seems easy to find for a particular q of x. Okay, so here is another. So f of x equals 4 by 5 is a particular solution. Okay, very easy solution. You can check that 4 by 5 will be a solution here. Likewise here, generally also you can do. If q of x is d, f of x is you can guess that to be d by c, right? So that will be the solution here. So the d by c will be the solution for the general case, right? So it's easy to see. So supposing q of x is sinusoid, okay, so you remember we were thinking of sinusoid as a possibility for q of x, right? So how do you find particular solution with sinusoid? In the circuit example, we are also interested in sinusoid functions. Okay, I'll consider a more general sinusoid, not just sin x, I'll consider sin x plus cos x. Okay, so you may also have something multiplying x here, but that's a small variation, we can deal with it quite easily. So q of x is u sin x plus v cos x. Okay, so here my guess will again be for f of x r sin x plus s cos x. R and s are different constants. Why is this a good guess? See, at the right hand side, I want a linear combination of sin x and cos x. Okay, so that means f of x also I can guess a linear combination of sin x and cos x. The reason is, see, if I do a derivative of this, I'll again get a linear combination of sin x cos x. Right? If you remember the properties of sin x cos x, if you differentiate, sin x becomes minus cos x, sin x becomes cos x becomes minus sin x. Once again linear combination of sin x cos x. If you do one more derivative, you will get another linear combination of sin x cos x. So linear combinations of sin x cos x under derivative remain the same. So if I want a linear combination of sin x cos x here, particular linear combination, I can simply guess another linear combination here and I should get a linear combination at the end. Okay. So notice how these properties of these functions are helping you in designing particular solutions for these kind of differential equations. So this is the guess here, and here's an example. I'm going to show you a case where this is just sin x, u is equal to 1, v is equal to 0, so sin x. So I'm going to guess f of x equals r sin x plus s cos x. Plug it in here. I told you what will happen, right? F of x 5 times r cos x, r sin x plus okay, what did I do here? Okay, so I've substituted f of x equals r sin x plus s cos x. So 5 times f of x is just here, right? That's okay. Then if I take a derivative here, I'll get r cos x minus s sin x. So 2 times r cos x minus s sin x, that is 2 times f prime of x. Okay, then plus another derivative. If I do another derivative here, minus r sin x minus s cos x, that is f double prime here. So the sum of these three should be equal to sin x. So what is this? So if you look at the coefficient of sin x here, you get 5r minus r, which is 4r minus 2s. So 4r minus 2s should be equal to 1. So the coefficient of sin x, what is multiplying sin x, should be 1. What about the coefficient of cos x? It should be 0 because there is no cos x. I don't want any cos x on the right hand side. It should be 0, and that will be 5s minus s is 4s, and then you have a 2r here. So 2r plus 4s equal to 0. So you just solve for r and s. You get r equals something, s equals r equals 1 by 5 and s equals minus 1 by 10. So my solution here, particular solution here is 1 by 5 sin x minus 1 by 10 cos x. Isn't that nice? Okay. So you get a very nice solution for this particular case, and you can guess a solution for both of these things. Okay. So what we have seen now is if you have a non-homogeneous equation, I am able to guess a particular solution very easily, and I also am able to solve the homogeneous equation. So let me see how to solve the homogeneous case. Okay, let's take this example here. F prime of x plus 2f prime of x, 2f double prime of x plus 2f prime of x plus 5f of x equals 4, right? What I'll do, instead of taking this example, I'll go back to my previous examples that I had for the 3 cases and quickly show you, at least in one case, how that solution works out. Okay, so we were able to solve this guy here, the homogeneous case. Let's solve the same equation for the non-homogeneous case. Okay, so what is this equation? I have f double prime of x minus 6f of x, f prime of x plus 8f of x. Okay, let's say I have this equal to 0, and let's say my initial condition is something, right? F of 0 equals f prime of 0 equals 1. Okay, the same initial condition. Instead of 0, I'm going to put, let's say, 4 here or 5 here. Okay, let's put 5 here. Okay, so what is my homogeneous equation solution? We have seen this already. For the homogeneous equation, okay, my solution is c1 e power 2x plus c2 e power 4x, right? So 2 and 4 are the solutions of the characteristic equation. So you get c1 e power 2x plus c2 e power 4x. So the homogeneous case, that is the solution. What about a particular solution? Okay. I know I am going to guess f of x equal to some constant, right? And what should the constant be? It should be 5 by 8, right? A particular solution is 5 by 8. Okay. So, what is the general solution? Okay. The general solution is going to be f of x equals 5 by 8 plus c1 e power 2x plus c2 e power 4x. As simple as that. Look at how easily it comes about. You find the homogeneous solution with c1, c2. You find the particular solution by guess for a constant. I know this needs to be a constant. The constant will be 5 by 8. So that these things will go to 0. If it's a constant, you will get that. So now you use the initial condition. F of 0 is equal to 5 by 8 plus c1 plus c2, which needs to be equal to 1. F prime of 0 is 2c1 plus 4c2 equal to 1. You can just solve this. I'm not going to solve this for you. You solve this and plug it back in, you get the answer. Okay, so you solve this, find c1, c2. As simple as that. Okay, I hope you saw this little solution here. So let's look at the next case. The next case is really easy, the repeated roots case. I'm not going to do this for you. Maybe what we can do, an interesting case, is to do this itself, or maybe we can do the repeated roots case for a sinusoidal input, sinusoidal forcing function. Okay, so let's change this forcing function. So I have f double prime of x minus 6 f prime of x plus 9 f of x equals, let's say, sine, I'll keep some factor here, I'll put omega naught t, so omega naught x. Okay, so this is my factor. Let me leave the coefficients alone for now. Okay, so once again, the homogeneous case is easy to see. Homogeneous is what? Solution is c1 e power 3x plus c2 x e power 3x. This is a homogeneous. What about the particular solution? Okay, I'm going to guess my particular solution to be r times, so f of x equals r times sine omega naught x plus s times cos omega naught x. Okay, so this is an important thing to remember. The omega naught will show up here. Okay, that's important because that's how you will get these things. Now, if you plug this back in here, notice what's going to happen. Okay, I'll have a 9 times r sine omega naught x plus s cos omega naught x. This whole thing has to be equal to sine omega naught x. Okay, so if I do a derivative, I'm going to get minus 6 times. If I do a derivative here, I'll get r omega naught cos omega naught x. Okay, notice how that omega naught enters the picture, plus or minus s omega naught sine omega naught x. Okay, this is again just using the properties of differentiation, the chain rule. Okay, finally, if I differentiate it once again, I'm going to get r omega naught minus r omega naught square cos omega naught x. So notice how omega naught enters the picture here, minus s omega naught square, sine here, sine omega naught x, and then cos omega naught x. Okay, this is the equation. So now I want the coefficient of sine omega naught x to be 1. So what is the coefficient of sine omega naught x? You see here, you will get r here, r here. So r times 9, okay, r times 9 minus omega naught square. Okay, here you have minus s omega naught, right? So these are the 3 sinusoids, minus s times omega naught equals 1. And then what about the cos one? You have s times 9 minus omega naught square. Okay. Oh, I forgot the 6 here. I'm sorry. Plus 6. I'm sorry here. I just made the multiplication mistake here. Minus 6 needs to multiply this. So you get this here minus 6r omega naught equal to 0. Is that okay? I hope these two are correct. So you get here from this equation that so you have to solve these two equations. So I'm just going to quickly solve for you. S equals 6 omega naught r divided by 9 minus omega naught square. Okay, that's what S is, isn't it? So you plug this back in here, you will get r times 9 minus omega naught square plus 6 times, right? S will be 6 omega naught squared, right? So 6 instead of x, I'm putting 6 omega naught square by 9 minus omega naught square times r equal to 1. So, if you solve this, you are going to get r to be, from here you will get r to be equal to, okay, multiply throughout by 9 minus omega naught square, 9 minus omega naught square by 9 minus omega naught square whole square plus 36 omega naught square something, right. So, 9 minus omega naught square the whole square plus 36 omega naught square. Okay, so you will get something, some quadratic involving omega naught power 4, that is going to be r. From here you substitute back here, you will get s. So, you will get this solution, let me write this as some r1 sine omega naught. So, I will call this r1 and then this one is s1, r1 sine omega naught x plus s1 cos omega naught x. This is some formula involving 9 and omega naught square, you can simplify it in the particular case. So, what will be the general solution? Solution is going to be particular plus this guy, right. So, it will be r1 sine omega naught x plus s1 cos omega naught x plus c1 e power 3x plus c2 x e power 3x. Okay. So, now depending on how this c1, c2 and 3 and all work out, this will be the general solution, and given an initial condition, you can find c1 and c2 based on this. Okay. I hope you see this. So, the final problem, I also want to show you what happens in the complex conjugate case, or maybe I will keep the complex conjugate case for the next one. So, we are going to see a very important application here, which is we saw the complex conjugate case and then we saw the homogeneous case, and one of the very important applications of these solutions is the RLC circuit. RLC circuit with the DC source and RLC circuit with the AC source. In that case, you will get complex conjugate roots more in some cases. So, I will take up that example when we do that later on. Okay? That concludes this lecture. Thank you very much.